Thank you, everyone, for being here and attending my paper. Let's see, here's an outline of my talk. I'm going to talk a little bit about neutron behavior, give an example reactor, and understanding the behavior within the apparatus, and I'll show you some equations. I'm also going to show you some spreadsheet calculations. These are the things that I do. And then we're going to talk about Monte-Carlo simulations. And these are the things that Sven and John have done. I'll make a comparison of those two. I'm also going to talk about neutron exposure and neutron detection. Then we're going to look at some gamma rays, gamma exposure. And then I'm going to talk about why Monte Carlo simulations are necessary, and then we'll go on to conclusions. For over 35 years, it has been believed that low-energy nuclear reactors, LENR, do not emit large quantities of neutrons. However, it's difficult, as we all know, to conceive of a conventional LENR process that occurs without emitting large quantities of neutrons and gamma. Many novel and imaginative models have been created in an effort to keep neutrons out of LENR theories. Unfortunately, some of those models are in violation of known physics, and regrettably, this has led to the conventional scientists claiming that LENR is a pseudoscience. And this has been an ongoing issue of non-acceptance, and it seems to be directly related to neutrons. So I want to try a new approach. That's been my approach, is to try something new. Rather than creating some sort of novel explanation to get rid of those neutrons, the approach that I prefer is to start with a conventional explanation and explore some other and hopefully better reasons for the lack of neutron detection. So let's take a look at understanding neutrons in a serious matter. This is an example reactor, typical electrolytic reactor. I have a PD core, let's see right here, lithium electrolyte here, Pyrex glass here, a water bath, and then more Pyrex glass here. Now the height of this might be a little bit short. I just have 25 centimeters, but the rest of this looks pretty typical for a electrolytic reactor. When the neutrons are emitted from the PD core and they're still within the LENR apparatus, they're going to scatter, they're going to slow down, and they're going to react. And all of this happens within the entire apparatus, not just within the core. Only a very small percentage of the neutrons will escape the experimental apparatus for a typical electrolytic LENR surrounded by a water bath. But how many actually do escape? Here are the equations for it. I have an intensity, the I, which is a function of distance, for a point source, and as you can see, it's an exponential function of the distance, plus something called the mean free path, lambda total. Now, lambda total is the average distance traveled before there is some sort of interaction. And as you can see here, it is the reciprocal of the sum of the reciprocals for lambda scatter plus lambda reaction, where lambda scatter is the mean free path for scattering, and lambda reaction is the mean free path for all neutron-induced reactions, and it is for all elements, all isotopes, but for one energy. So for example, if we looked at lambda reaction for water, I have for H2O, and I have for deuterium, where that H is a 1, and I have where the H is a 2, and the oxygen is going to include all of the isotopes. So the sum of all cross sections for all of the neutron scattering, sigma react. This is for all of the reactions that occur. This equation is for all reactions between the neutron and the nuclide, but it's at one specific energy. I do my spreadsheet calculations. This is an example of a working spreadsheet. I don't expect you to read it. I just, there are equations in each one of these little boxes. I have 9 such spreadsheets looking like this, but at different energies. And these spreadsheets are used to calculate how many neutrons escape the apparatus. And like I said, behind each one of these teeny little boxes here is the equation and a number. Here are the rest of those 9 spreadsheets. And I show you this not because I know you can't read this, but I want to impress upon you that this is not a quick and easy calculation by any means. Let's talk about the results. The total that react for the neutrons is going to be about 30%. About 68% will thermalize in the water bath, and then they're going to react in that water bath. And about 2% are going to escape the apparatus. Mostly, those are going to be at high energies. Let's look at what the Monte-Carlo simulations say. That was my spreadsheet. So Monte-Carlo simulations is a compilation technique using repeated random sampling to obtain numerical results. And it's widely used in various fields of science. Monte-Carlo methods are recognized as one of the most important and influential ideas of the 20th century. And in principle, Monte-Carlo methods can be used to solve any problem having a probabilistic interpretation. Here's what was simulated. It's a reactor very similar to the size that I did in the spreadsheet. The only difference is they had a much longer, higher water bath. And there were 25 nuclear processes that were simulated. Here's some of them, here are the rest of them. You can see a lot of processes were simulated. Here are the results, where they occurred, and how many. Here are the generated subnuclear particles shown here. There's more. Here are the generated elements, isotopes, and high energy states. There's more. I'm just going to click through these. You can see there were a lot of particles, isotopes, etc., that were shown. And I show this to you just to impress upon you that this was a very thorough and complete analysis. Everything and every possible reaction were considered in the Monte-Carlo simulations. Here are the results. Simulating a burst of 1 million neutrons going through the apparatus starting at 10 MeV. We find the distribution looks like this. Now this is a log-log scale. Most of the escaped neutrons are at high energy up here. Like I said, this is a log-log scale. Most of this is very small count. So roughly about 12% escape for the 10 MeV, just for the 10 MeV neutrons. Let's take a look at a burst of 1 MeV neutrons coming through that same apparatus. It looks like this. 50 of them came out. Okay, out of 1 million, 50 came out at a very low energy. If you add both the 10 MeV and the 1 MeV together, the average is 0.3 MeV neutrons. I'm sorry. And this was less energy than what I simulated in this, or calculated in the spreadsheet. But the total percentage that escaped for the spreadsheet was 2.1%, whereas for the Monte-Carlo, it was 6%. And that's only a factor of 2.8. Not a big deal. I'm not off by factors of 20 orders of magnitude. I'm not off by 1 million. I'm not off by 100. It's a very small amount. Let's keep going. Let's look at neutron exposure. So what I have here is the number coming out of the apparatus, the energy that they come out at, and the total energy, and the neutron energy coming out in joules. I'm sorry. No, that doesn't help either. Okay, the total neutron energy absorbed by an average person a meter away for a 1-watt reactor. And then let's look if that person is an average size person, you're going to get 1/5 of a harmful dose if they stand right there next to that reactor for an hour. That's what I calculated for my spreadsheet. The Monte-Carlo simulations calculated something similar. 1/37th of a harmful dose is all that they're going to get. A harmful dose is not the lethal dose. That's just, you might get a little headache, you might feel nausea or some kind of fatigue. So it's a small fraction of a harmful dose. So let's look at a neutron detector. Now here I've got my reactor, the same reactor we saw earlier. And I've got my detector, it's 1.5 centimeters away from this Pyrex. This blue part here is the moderator tube. It's a cylinder. I show it as a square, but you're looking at it sideways. It's a cylinder, and here is the gas chamber, the He3 gas chamber. The diameter of the moderator tube is 5 centimeters. And now the number that enter this moderator tube is the number that escaped, multiplied by the area of this aperture here, and then divided by the surface area of this imaginary sphere of 35 centimeters. And that's going to be something about a factor of 1/800. Now, there are some common misunderstandings about neutron detection. Can we just measure background radiation and call this calibrated? No, because actually you're maybe measuring some of those background neutrons, but what you're really measuring is the noise in the amplifier electronics. You're not measuring real, and you're nodding your head, thank you. It actually means nothing, but yes, you do have to subtract that out. Now, can we assume that one count is equal to one neutron? No, because it depends on the external capacitors that you use, the resistors that you're using, the threshold voltage of the amplifier and the trigger that it's set to, the density of the H3 gas, and the geometry of the gas chamber, and the detector efficiency. Can we use a homemade neutron detector like a gold coin and then declare there are no neutrons? No, you really need to use a commercial neutron detector. So there are some inherent problems with neutron detection. Most of the neutrons coming out are at very high energy, 2.45 MeV or 14 MeV. He3 detectors cannot detect those. They cannot detect these high energy neutrons. They need to be moderated down to 0.026 eV. And that's an order of 8 magnitudes difference in energy. So you need a moderator tube in order for that He3 detector to work at all. So you need to know two things if you're going to calibrate your detector. You need to know how many neutrons are being generated per second, and you need to know their energy. So for fission reactors, this is not a problem. Fission engineers, they know exactly how many neutrons are coming out of their reactor, and they know exactly what that energy is. And they're not worried about measuring teeny little small amounts, quantities of neutrons, and the neutron detectors are not designed for small numbers. However, for LENR, these two are a problem. We don't know what their energy is, and we don't know how many are being made. So it is a problem. Let's take a look. I said I needed a moderator tube. Let's take a look at a moderator tube. So here is that same little blue cylinder, And here's the gas chamber that we saw earlier. And I've got lots of neutrons. These little red lines here are vectors. This is in 3 dimensions, and they're all coming into that moderator tube. Most of them are high energy. You can see that by the large vectors. When they go into that moderator tube, they're going to scatter on these H1 atoms. Now, when they do scatter, they only retain about 37% of their energy. At high energies, essentially no neutrons are going to react. So here they are scattering in all dimensions, in 3 dimensions, in the He3 gas. They don't enter. If they do enter the He3 gas chamber, like you see here, they're not going to react. Why? Because they're too energetic to react. Most of the high energy neutrons are going to escape, and this is just with one scatter. There may be some reactions, and it would be when I take a neutron and an oxygen-16, it forms an alpha plus carbon-13. This is what it looks like after these scatters. I don't have a whole lot left. Okay, what is left? And this is just after one scatter. Now, those that are escaped the moderator tube, they're gone. They're not going to be detected.
Yeah. You have 5 minutes, okay.
Oh, dear. Okay, so let's go and take a look at this. More of these are going to scatter. They keep scattering. I am now at intermediate temperature energies. Some of these might react. Some of them are going to get stuck. If they do eventually enter the chamber, a few will react. What do the simulations say? The spreadsheet calculations say that if I start out with 4 times 10 to the 11th neutrons being generated in my reactor, I may detect the number that react in that gas chamber may be 2 to 3 neutrons. The Monte-Carlo simulations said 0. It's hard to make a comparison, a direct comparison, but you can see they are very much in agreement with each other. Now, the big thing is when you vary the radius of that neutron detector, look at how this changes, this ratio of how many entered that detector versus how many were entered that moderator tube. It changes by 9 orders of magnitude as I change that diameter from 2 to 20. So I hope you can understand why there's so much variation from experiment to experiment and why it's so difficult to measure these things. This is it right here. 9 orders of magnitude just because of a little diameter change. Let's look at gamma exposure. For the spreadsheet calculations, I calculated you're going to get about 1/17 of a gray for an average man standing next to a 1-watt reactor 1 meter away for 1 hour. The Monte Carlo simulations said it's going to be about 1/5 of a gray. Okay, where gray again is the harmful dose. So what does that mean? It means if you're running an electrolytic reactor with a water bath and it's at 1 watt, you don't want to stand next to it for an hour real close. And if you are doing that, you may want to give it more shielding, a little more distance, and ignore the people who say, oh, no, there are no neutrons. I would, it's my body, you want to save yourself. So Monte Carlo simulations are important because it is very difficult to simulate, to actually do a proper calibration of a neutron, an LENR. In fact, it's pretty much impossible. In order to do a proper calibration, you want to simulate with a Monte Carlo simulation that replicates your apparatus and your neutron detector. And the Monte Carlo simulation is really essential. So review, this is what we talked about. And neutrons are created in LENR. They scatter and they slow down, they react. They're very difficult to detect. If you get even a few counts above the background, it's an indication that neutrons were created in the reactor core, and this is indeed commensurate with the heat production, confirmed by Monte-Carlo simulations. To understand LENR, you don't need novel concepts, especially if they're in violation of known science. Rather, we just need to understand that very few neutrons are going to be detected in an LENR. Thank you. Any questions?
Okay. Thank you very much. Any questions or comments?
Okay. The problem is that your conclusion is slightly wrong. If there is any, you should say, if there is any neutron, you cannot measure it. That's all. But we are not sure there are neutrons. The question is, they are measured excess heat in correlation with helium-4, and there's a good
Right.
correlation. So where are the
There's no
neutrons coming
correlation.
from?
No, there's correlation in my model, which I'm not talking about my model here, but in my model, there's a direct correlation between excess heat and He4. And here, I'm not talking about that model, but here I'm talking about that detecting just a few neutrons is commensurate with the heat.
No, because if you do that, if the reaction is producing neutrons, the heat will be correlated with the amount of neutron absorbed by the cell itself is very limited because it's very small. So most of the neutrons will warm up
I see what you're saying.
You see what I mean?
Most of the heat comes from, and I'm not talking about the primary and secondary reactions, those are previous talks, but most of the heat in the cell comes from the primary and secondary reactions. And I say that's commensurate with the He4 production. The amount of heat that the neutrons generate in the entire apparatus is a small percentage. It's like 5%.
Yeah, but the experiments show that the correlation between helium-4, the amount of energy produced, means that DD produces helium-4, not neutrons.
Oh, no, you have to have the two primary and secondary reactions. And I'm sorry, I didn't show those here, but it's the two primary and secondary reactions will produce helium-4 in a commensurate amount as the heat. And I've shown that before.
We'll talk about that later.
I'm not talking about that here. But yes, helium-4 is produced, and it's in the same ratio as what you would expect. Yeah.
Okay, so
Yes.
I wanted to ask a question. So in such type of experiments, question that what is the ratio between the thermal neutron fluences and the fast neutrons? So basically ratio of the populations of the thermal neutron and the fast neutrons.
You mean when they're initially created or when they are emitted?
When they're just exiting the cell so that we can use the detector.
Exiting the palladium or exiting the entire...
cell. Exiting the cell.
The water bath.
Beaker, yes. Yes, bath.
Yeah.
So that's where we are going to put our detectors. So specifically, like
I think I said 2% are going to exit the cell.
Okay.
And most of those are high energy.
Okay.
Right? And I'd say at the lower energy, all the way down to thermal, like the 0.026 EV, very, very few are going to exit.
Okay.
So essentially zero.
Okay, so in case the major population is of fast neutrons,
Right.
do you have any comments on why helium-3 fails to consistently measure the neutrons? Because it is the moderator around the helium-3, the plastic polyethylene sheet or the wax around the helium-3 is supposed to thermalize the fast neutron population.
Right, but most of the fast neutrons escape, especially if there's a very narrow diameter of that moderator. They're going to escape. As I showed you, I had to zip through that, but yeah, the neutrons are going to escape that moderator tube. And you think, well, why do they design it so poorly? And as I said, fission reactors, fission engineers don't care because they already know how to calibrate that.
So what you are suggesting is that one should use a bank of detectors. That would certainly
That
increase.
is exactly what fission reactors do.
Okay,
Yeah, yeah.
okay.
They use they probably have, I don't know, 12 or so going around their reactor. Yeah,
Okay, thank you.
yeah. Any others?
Any questions? Okay, please.
Yes, hello. Thanks for the talk. I guess my question was to follow up, like, so you showed that the thicker moderators showed a higher detection efficiency. Is that correct? Or did I misunderstand?
That's correct, yeah. A thicker radius of that moderator tube, yeah.
Okay. But,
And I went from 2 centimeters to 20 centimeters.
right.
yeah.
And that's because the fast neutrons don't get detected in the helium-3 chamber.
That is, the reason there's such a variation is because not as many neutrons are going to escape that fatter moderator tube.
Okay. So, yeah, okay. But is there some point where it's too much moderator and then it actually, you lose neutrons to?
Yes.
Oh, okay.
Yeah, in fact, I didn't talk about it because I was going too fast.
Yeah.
But if you have a moderator tube that's too long, I simulated all the way out to 20 centimeters, something like this. It'll go up. It's not as drastic of a curve. It's not 9 orders of magnitude, but it'll go up and then it'll start to go down.
I see.
Yeah, because the neutrons just can't make it to that gas chamber. They get stuck.
Right, I see what
Yeah.
you're saying. Okay.
Yeah.
Okay, that makes sense. I was curious. Thank you.
Okay, thank you.
Please.
Thank you very much for your very nice talk. I have a question because you're arguing that the neutron numbers can be much higher than usually the people assume. But the point is, in the cold fusion experiments, electrolysis experiment, heavy water electrolysis, they measure a very small amount of helium-3 gas, compared to helium-4. So it is not because the neutrons are escaped, because helium-3 will remain in the cell. So it is something what is really absolute.
Right.
Something what is not depending on the neutrons escaping.
Yeah, I'm sorry, in my previous talks that I've done, I talk about primary and secondary reactions. The primary reactions are the 2 reactions that are common for deuterium plus deuterium, where you create helium-3 and you create tritium, right? And a neutron and a proton. Those helium-3 and the tritium react with another deuterium, a deuteron. And about 100%, maybe somewhere between 70 and 100% of the tritium will react with a deuterium. About somewhere around 40% of the helium-3 will react with another deuterium, and that creates the helium-4. So I get the helium-4 from those secondary reactions. That will burn up a lot of the tritium, and that burns up a lot of the helium-3. Now, why we don't detect so much helium-3, I think that's because it's difficult to detect and difficult to separate out. Yeah.
I think the sensitivity for detection is very good, in the experiments. So it is not the problem of sensitivity or accuracy. It is really very good. So I think there is really one of the most important observations that in the DD fusion you have probably less protons or neutrons than helium-4, because helium-4 is really correlated. There is a very small cell that you have the gas emitted, and the people measure it. So it is what the people said for many years. Maybe they are wrong, I don't know. They said that this heat excess is correlated to helium-4 gas.
Right.
And helium-3 or tritium is much less. So
Right.
it is, of course, there is of the fundamental interest or importance to measure these branching ratios, I think.
It would be very good to have a very precise measurement of helium-3. Yeah, because there should be more in the cell than what I've seen reported. But that is another talk. That's not the talk that I'm giving here. That's talks that I've given previously, so sorry about that, but I didn't even mention them.
Okay, so now this session is closed, and announcement from Chairman. Thank you.